Now, let us talk about Boltzmann distribution back again. We have already derived Boltzmann distributions. Remember that when we calculated the particles in different levels for different distributions, and then calculated how many particles are there in level 1, level 0, level 2 and things like that, and then we showed that it by fitting, by numerical fitting, that it follows something like e to the power minus b a into e to the power minus b epsilon. So, that b and b, one can show that it is nothing but 1 by kBt, that I also mentioned. So, I will just remind you, so that is what we talked about, and that is called probability. So, probability of particle to occupy ith level is nothing but number of particle in the ith level divided by total number of particle, Ni by n, and that is already I have shown the derivation in which we showed that it is nothing but e to the power minus Ei by kBt. So, energy of the ith level divided by kBt, that is nothing but e to the power minus, remember we talked about beta E, it is nothing but the same thing, beta Ei we said. See, this b is nothing but 1 by kBt. So, it will be Ei by kBt, and that is what it is mentioned here. And there was a here, and that a is nothing but a normalization constant, and you can normalize. For normalization constant, it must be this one. So, that when you sum over the whole quantity, then it becomes 1, because it is a probability. You know the probability, when you sum over the probability has to be 1. So, when you sum over this particular quantity, it has to be 1, and therefore, this quantity in the denominator is just nothing but normalization constant, and that is normally denoted as q, and this q is called partition function. This partition function therefore, is nothing but just a number. Why it is a number? Because it is a sum of exponentials of energy values basically. So, if I have let us say 3 different energy values, let us say I have 0 energy value, 1 unit of energy value and 2 units of energy value, and let us say I have 2 particle in the 0th level, 2 particle in the first level and 1 particle in the second level. How can I calculate my partition function? So, I have to calculate my partition function by taking into account of this expression that it is e to the power minus Ei by kBt. So, in my partition function I will have e to the power minus 0 by kBt plus e to the power minus epsilon by kBt plus e to the power minus 2 epsilon by kBt. That will be my partition function. And what is my probability? My probability will be P 0 will be 2 by 5, P 1 will be 2 by 5 and P 2 will be 1 by 5, okay, because there is only one particle in the 2 level. Okay. Is it clear? Ni by n we have used, and we have used the definition of partition functions to
is equal to Ni by n.
Ni by n.
N is total number of
Ni is the number of particles in ith level,
and n is the
total number of particles.
Then how this exponential sum gives total number of particles?
No, exponential sum does not give it, it gives just Ni by n is denoted as here, because Ni by n was fitted to this expression. So, Ni by n was fitted to e to the power minus b Ei, it was fitted to that, and this is a normalization constant. Why? Because such that the sum over Ni by n is nothing but 1, right. So, that means sum over a e to the power minus b epsilon is 1, a is just a constant will come out. So, a is e to the power minus b epsilon I equal to 1. So, 1 by a is nothing but sum over e to the power minus b epsilon I, and that is what is shown here. So, this can be written as e to the power minus b epsilon I by 1 by a, and 1 by a is nothing but this one sum, it is just a normalization constant. Okay. Okay. So, now this q is called partition function, and with this probability the entropy will be defined by Kb sum over Pi ln Pi. So, I can just show you that in a very brief derivation. So, we know that W is n factorial by n 1 factorial, n 2 factorial, n 3 factorial and things like that, which means that I can write that as n factorial by product of Ni factorial, correct. So, now we know that entropy is Kb ln W, which means entropy is Kb ln n factorial by product of n I factorial, which means I can write that as k b ln n factorial minus sum over ln n I factorial. The product becomes sum when we use ln. In case of ln, the product becomes sum. So, that is why it is a sum. Now, once we have done that, we can write that as k b n ln n minus n using Stirling's approximation minus we can write as sum over I n I ln n I minus n I, that I put as sum So, now I can write again k b n ln n minus n minus sum over n I ln n I plus sum over n I. Now, I will continue the derivation here. So, S equal to k b n ln n minus n minus sum over n I ln n I plus n. Okay. So, this n and this n cancels each other, giving us k b n ln n minus n I ln n I sum over. Now, how can I do that? Now, I can write the n as sum over n I ln n minus sum over n I ln n I. Now, I write k b n I take common n I ln n minus ln n I. Now, equal to k b sum over n I ln of n by n I equal to, now let us take a minus sign, minus k b n I ln n I by n. Let us multiply and divide by n. So, minus k b n n I by n ln n I by n equal to minus k b n p I ln p I, and that is what is the proof. So, we see that whenever we so this for this case, this is only for one particle. However, for n particle we should write as minus n k b p I ln p I. If you have one particle, then this is the formula to use, and if there are n particles, then this is the formula to use. So, now we are going to make use of this particular formula to understand something. So, remember, note that this p I we are talking about probabilities, normalized probabilities, that means for only one particle this formula is used. Okay. We can always use normalized probabilities, and then it will be scaling as the number of particles increasing. For example, whatever the value we get for 1, you multiply by the number of particles and you get for that many number. For example, you get entropy typically in per mole basis. Now, if you have 10 mole system, it will be 10 into that. It is something like that, it is a per particle basis, and you can, if you have Avogadro number of particle, multiply by the 6.023 into the 23 and you will get the entropy per mole. Okay. Now, so I will just show you that how this particular formula of p I ln p I. So, we have done the derivation starting from W, and now we go back to the W. So, for isolated system or for systems where energies are all equal, or let us say, or let us say for or degenerate system where all the energies are same, in that case you know that probability is proportional to the energy. So, if all energies are same, then I can write, instead of E I can write simply E for all probabilities, and it will be nothing but e to the power minus E by k b t by q or 1 by W. Why? Because all probabilities are same. So, if there are W number of microstates possible, then the probability of each microstate will be 1 by W, because they are all equal. And once I put now 1 by W in this particular formula, then I can write it this way, because Pi is 1 by W. So, 1 by W ln 1 by W. Once I do that, I get back my Kb ln W. So, Kb ln W is very general expression, and Pi ln Pi also is general, where the probabilities are different, but Kb ln W is simply can be used for whatever. So, this is again the postulate which essentially So, how did it all start? So, we started with Kb ln W, then we said W is n factorial by n factorial, n2 factorial and all that for distinguishable particles, and from there we got back the Boltzmann statistics, and from there again we got back W when all the microstates are all equal. So, it only means that if the energies are all equal, we are going to get we are going to simply count the number of W, and that will give us the entropy. However, if energies are not equal, then we cannot just simply count the W, we have to use this particular formula, because then the number of microstates will be weighted by how probable they are, and that is where the distinction comes when systems are distributed in different levels differently. So, if Pi is the probability, so if Pi is more, then the probability of that microstate will be more to form. That means the weights of that particular microstates will be even more. So, that we have to understand. So, for example, if I buy 4 apples and 2 banana, and let us say 4 apples, each of them cost 10 rupees, and banana each of them cost 5 rupees. So, 4 apples is 40, 2 banana is 10, so 50, and divided by I have 6. So, it is definitely more weighted by the apples and then the bananas. So, the probability of apple being there is 4 by 6, whereas banana being there is just 2 by 6. So, therefore, when you take an average of an apple and banana, I can simply take 10 as the price of apple multiplied by 4 by 6 plus 5 multiplied by 2 by 6. That will give rise to the value, same value that we can get by adding all of them together, 10 plus 10 plus 10 plus 10 plus 5 plus 5 by divided by 6. We will get the same result if we just multiply 10 into 4 by 6 plus 5 into 2 by 6. So, that is an example of weighted averaging, and weights are nothing but the probabilities. Okay, let me just derive that how we are getting the Kb ln W. So, we know that S is minus Kb Pi ln Pi. Now, Pi we know as e to the power minus beta Ei or Ei by Kbt, e to the power minus Ei by Kbt by Q, some value, some constant value, which is the normalization constant, that is the Pi. Now, if all energies are equal, that means E1 equal to E2 equal to E3 equal to E4, all states are equal to E, then I can write Pi as e to the power minus E by Kbt by Q, which simply means that this is a constant term, this is a constant term, and which means this is nothing but a constant term 1 by W. I can always put that, I can write one more step though, so that it will become clear. I can always write that as 1 by Q into e to the power minus E by Kbt, or I can write 1 by W. 1 by W here is nothing but Q into e to the power plus E by Kbt. Okay. So, we know that Pi is 1 by W. So, now let us put that here, minus Kb 1 by W ln 1 by W. Now, when there is a minus and 1 by W, minus will become plus and it will give us 1 by W ln W. So, now we know that W is a constant. So, let us take out W and ln W, and I will have a sum of 1 going from I to W. So, which will give me ln W multiplied by W, and W cancels, giving me the Kb is also there here, giving me Kb ln W. So, now we got Kb ln W. Now, let us see that how this Pi, which is the probability of being in the ith state, affects or helps us to understand that while the energy of a particular system remains constant, or for example, energy of the universe remaining constant, entropy keeps on increasing. And remember, we even discussed in our intro slides that while the energy is conserved, the distribution of energy is not, and that is an indication of increase of entropy. Okay, so let us understand through a simple problem. So remember, we discussed about 3 particles distributed in 4 different energy levels, and we saw that we were getting 3 possible distributions. One is distribution A, where the W was number of possible distributions were 3, and then the distribution B, where number of possible arrangements or number of microstates were 6, and the distribution C, where the number of microstates was 1. The total W was 10, and the entropy obtained from that was kBln 10. Now let us see that with these new ways of calculating the number of particles in different levels, what kind of entropy values we get. So in order to calculate that, let us see that what is the probability of finding particle at 0th energy level. You see that in the distribution A, there are 2 particles in the 0th energy level, and since there are 3 possible ways of doing that, so we can write as 3 into 2. There is 1 particle at 0th energy level, but there are 6 possible W's, so therefore that will be 6 into 1, and there is no particle in the 0th level in the distribution C. And how many total number of particles are there? So as you can see, there are 10 possible distributions. Each distribution has 3 particles, so there is total 30 particles. So if I calculate that, it will be 6 plus 6, 12 by 30, giving us 4 by 10. Now let us calculate the same way the probability of finding particles in level 1. So as you can see, there is no particle in distribution A, but there is 1 particle in level 1 for distribution B, and there are 6 possibilities, so 6 into 1. And there are 3 particles in level 1 for distribution C, and there is only one way of getting that, so therefore we get 3 into 1. So and divide by 30 again, so we get 9 by 30 or 3 by 10. Let us calculate now probability of finding particle in level 2, and you can see that in distribution B there is a particle at level 2, and there are 6 possible ways of doing that, so I will get 6 by 30, or 6 into 1 by 30 you can say, so 6 by 30, and giving us 2 by 10. And finally let's calculate the probability of getting a particle in level 3, and you can see that there is 1 particle in level 3 for distribution A, which has 3 possibilities, so it is 3 into 1 by 30, so 3 by 30 or 1 by 10. Now first thing to notice is that the sum over pi's I going from 0 to 3 is equal to 1. As you can see, 4 by 10 plus 3 by 10 plus 2 by 10 plus 1 by 10 is equal to 10 by 10 or 1. Now to calculate the entropy, we have to use the formula minus kb sum over pi ln pi, which means it is minus kb then 4 by 10 ln 4 by 10 plus 3 by 10 ln 3 by 10 plus 2 by 10 ln 2 by 10 plus 1 by 10 ln 1 by 10, and that is the entropy for 1 particle. So we should write as S by n or S by 3, n equal to 3 we know, right? So now let us calculate and see what is the value that we get. So 4 by 10 means 0.4 ln 0.4 plus 0.3 ln 0.3 plus 0.2 ln 0.2 plus 0.1 ln 0.1. We get minus 1.27, and we have to multiply that by 3, and there is a minus sign, so we have to put minus, so that much kb we are going to get 3 into, yeah, so 3.84, as you can see here, 3.84 is the value, 3.84 kb is the value, and kb ln 10 is, so we can calculate that ln 10 is 2.3, so that is 2.3 kb. So as you can see, it is not exactly same, it is 2.3, it is 3.84, but the reason is actually that our statistics is not enough to get exactly equal number, but they are pretty close. If you have many more number of particles, then one can get a much closer accuracy. Another closer similarity between these two number. Another point you have to note that these PIs are obtained only for the most probable distribution, because remember, when you get this formula PI, we had maximized the W under some constraints, and that gave us the most probable distribution, which is in this case is B. However, if we calculate PIs from only this distribution, you are going to get equal probability for 0, 1 and 2, which may not be the right one. For example, you will get for 0 you will get 1 by 3, 1 by 3 and 1 by 3, which will not give you the same number. So, this discrepancies will be there only for the smaller number of particles. For higher statistics, they are going to be the same thing. But now you know how to calculate the entropy both from the W, that means all possible distributions. You can calculate all possibilities and get that W, or you can calculate the probabilities of occupying a certain states and calculate the W. So, for example, that entropy is just not it's not only can be applied to atoms and molecules with energy, it can be applied to anything. For example, we can talk about the probabilities of students wearing socks. So, let us say these are the probabilities that out of 100 students, 20 students wear white socks on a given day, 10 students wear green socks, 30 students wear blue, 30 students wear red, and 10 students wear brown socks. So, probabilities of wearing socks for these students of different color is 2 by 10, 1 by 10, 3 by 10 and things like that. So, now we can use our entropy formula in order to calculate the entropy for this one also. Let us say the number of students is 100. So, 100 kb sum over pi ln pi, which is 2 by 10 ln 2 by 10. Let us forget the sum, because we are summing up anyway. 1 by 10 ln 1 by 10 plus 3 by 10 ln 3 by 10 plus 1 by 10 ln 1 by 10. I am not going to do the sum, but you can do that and see what value you get. So, the point is that one can in principle obtain entropy values for any probabilistic distributions. It need not be just energy, but then how meaningful that will be, that is a different question. But we can always say, right, that the entropy of the room is high, or the entropy of the situation is more. So, basically we are using in a sense that there are more possibilities that are happening around us, and that is a very loose way of talking about entropy. However, you should know that there is a subject called information entropy, where exactly this particular formula, except that kb part is used, where pi ln pi is the entropy of the information. So, and that is called Shannon entropy. So, that is very similar to this pi ln pi. So, now let us talk about that why entropy keeps on increasing in the universe and why that is the case. So, let us say that our energy distribution or energy of a particular system is always same 10, and or let us say the energy is 1, not 10, 1. It is not 1 unit, you can say it is just some value 1, you can say 10 also, I think 10 will be better. So, initially let us say all the 10 were in one particular place having one unique probability 1, that means all other probabilities of being there will be 0, and then it created a bias distribution of this kind, and then it created more bias distribution of this kind, and then it created a flat distribution of this kind. So, now let us calculate that in all cases what will be the entropy values. For example, in this particular case I have kb pi ln pi, which is 1 ln 1, and ln 1 is 0. So, it will give me 0. In this case I have minus kb pi ln pi. So, 2 pi's are 0. So, I have only half ln half twice, half ln half and half ln half. So, 1 ln half. So, 1 ln half is basically kb ln 2, and ln 2 is how much? Kb 0.693 kb, this particular thing. And now let us talk about this bias distribution. So, there it will be 1 by 3 ln 1 by 3 twice. So, it is 2 by 3 ln 1 by 3 plus ln 1 by 6 1 by 6 ln 1 by 6. So, 2 into 1 by 6 ln 1 by 6. So, this is the formula for this one, and let us see how much we get kb, and ln 1 by 3 is let us do the whole calculation, 2 by 3 ln 1 by 3 and 2 by 6 ln 1 by 6. Let us do the whole calculation here. So, 2 by 3 ln 1 by 3 plus 2 by 6 ln 1 by 6. So, you got minus 1.32 or 1.33 minus 1.33 giving us plus 1.33 kb. So, you see this distribution, this bias distribution has more entropy than this bias distribution, which has more entropy than this bias distribution. So, I will just write this. Now, let us calculate the flat distribution where everything is the same value, and what is the formula there? Again minus kb sum over 1 by 4 ln 1 by 4 terms I equal to 1 to 4. So, which is minus kb ln 1 by 4, which is plus kb ln 4. So, we have to just calculate ln 4 of this thing. Ln 4 is just the double of ln 2 because it is 2 squared. So, 2 times of ln 4. So, 0.693 is double, which is 1.39 approximately. So, it is 1.39 kb basically. Now, you see 1.39 is larger than 1.33. So, this one, the flat distribution has maximum entropy. So, you see everywhere the total energy unit has not changed, it is just that how it has distributed from this completely distributing in one place to becoming flatter. So, that is what happening with our world. Initially, you remember the Big Bang, the energies are concentrated in one dot, and as the time progresses, that energy is getting distributed in everything, and then more and more it gets distributed, more and more entropy increases, because it is just that the probabilities are getting flatter and flatter. And that is why we said that although the energy is conserved, the distribution is not, and as long as the distribution is not going to be flat distribution. So, when the entropy will be maximum? When everywhere there will be a equal population of energy units, or energy distribution will be completely flat, and that time the entropy will be maximum, and that is the time where our universe will come to equilibrium, and you know when that will happen, where if that happens, then every molecule will have to have the same amount of energy, and that will not allow the energy concentration in one particular place, like what you see in a organized system like a human being or plants or animals or any organized growth will be going against that particular flat distributions. So, that is why I say entropy is called the ultimate death, because it shows us the future of the complete stillness rather. Okay. So, now where is the use of this? Because once we know the probability, then we can use that probability and calculate the average values of a particular property. For example, when you talk about macroscopic property like energy, they are nothing but average energy weighted by the probability. When you talk about pressure, then it is nothing but average pressure weighted by the probability. When you talk about volume, as I said that 1 liter volume, when you say that a normal temperature and pressure 55.5 mole of water will have a volume of 1 liter, it does not mean it will be exactly 1 liter. It means that on an average it will be 1 liter. So, if you do a simulation with water, it will not be exactly 1 liter, it will be fluctuating, and that when you take an average, it will be then exactly 1 liter, and that is what we measure experimentally. So, all the macroscopic thermodynamic quantity which is written on this side are nothing but average over the microstates with the probabilities of a certain state as a weight function. Just like in quantum mechanics. In quantum mechanics, what we do? We calculate first the property using the operator. Once we get the observable using an operator, then it becomes, so this is the formula of an expectation value. Now, if let us say psi is the eigenstate or not even the eigenstate of A, what we get is that just I do one more step here, we get psi star A psi dx, then or d tau, whichever, if it is very general, let us call it d tau, and then what we get here is psi star psi A d tau. So, psi star psi is the probability just like our pi here, and A is the property just like our E here. So, you see here also what we are essentially doing is that we are calculating the average values weighted by the probability density psi psi star, which is nothing but this probability. Meaning, so what I am saying is that just like in quantum mechanics we get the expectation value from the probability distributions, we get similarly some expectation value based on the number of microstates and their energy values. So, that is where the connection between molecular thermodynamics and classical thermodynamics takes place. So, in one line, the statistical thermodynamics, the average value obtained from atoms and molecules is what we observe in classical thermodynamics, and that is what but we are not going to go into detail of that. You may look at other courses that are there. For example, in NPTEL itself there is a course by Shravani Tarabdar on Introduction to Molecular Thermodynamics, where you can get a little bit more detailed descriptions of molecular thermodynamics and its applications into understanding the realistic classical systems as well. So, then you can get a better idea of how to club both of them together. Here we wanted to just give a very brief outline of how to think about thermodynamics from atoms and molecules.